Last time we finished the method of finding the solution for the first order differential equation. Today we are going to learn how to find the solution for the higher order linear differential equation. So the general form of our n order linear differential equation is just shown here. And from this equation, a0, a1, and a2, a3 until an, and fx can be a constant or can be a function with x. Okay, could be number, could be any number, or could be a function of x. And a0 shouldn't be equal to 0 because it is an n order linear differential equation. If a0 is equal to 0, then it's not the n order. It would be the order of n minus 1. So from this equation, it's kind of the general form of the higher order linear differential equation. Okay, so if a0, a1, a2 to an is a constant, then we would call it constant coefficient, or we can call it the n order linear differential equation with constant coefficient. Otherwise, it is called variable coefficient. In this chapter, I will talking about how to find the solution of the n order linear differential equation with a constant coefficient. And at the end of the chapter would be the variable coefficient, but only some form that we call Cauchy-Euler equation, but not every form of the variable coefficient. Okay. And then, like the other chapter, which is called the power series, we will learn how to find the solution of the linear differential equation with variable coefficient. Okay. And for the higher order linear differential equation, if fx equals 0, then we call that equation homogeneous equation. If fx is not equal to 0, we call it non-homogeneous linear differential equation. The reason why I have to point it out for these two definitions because they have different answers, they have different solutions. Okay. First of all, we are going to talk about the homogeneous linear differential equation. I said, for the n order linear differential equation like this, and fx equals to 0, that is the homogeneous equation. We can find y n term, and we just assume that we have y1, y2 until yn. I just assume that y1, y2 until yn be the n solutions of this linear differential equation, the homogeneous linear differential equation. If all y are linearly independent to each other, then we can write down the general solution of this differential equation by putting the summation, writing down the y1, y2 until yn in the linear term, which is this equation, where c1, c2 until cn are arbitrary constants, mean any number, arbitrary constant. And this yc, we call it the general solution. The general solution is always be the solution for the homogeneous equation. So whenever we have the equation look like this, that fx equal to 0, that we call homogeneous linear differential equation, we have only one answer, which is we call general solution. And the general solution is writing in the term of the linear relationship of y1 until yn, where y1 until yn be the end solution of this differential equation. What does it mean by that? It means that if you know y1, y2, and yn until yn, and then you just put y1 in here, y1 makes this equation correct, because it is the solution of this equation. y2, when you plug it in this equation, you would find that y makes this equation correct. That means y2 is the answer of this equation. With the n order, you should find y for n solution. And the way to write down the final solution of this differential equation, you can do the linear relationship of y1 to yn, where c1, c2, and cn are the arbitrary constants. It means any constant. The next question is coming up that how do we know that all y that we find for this equation are linearly independent to each other? They said that, okay, that's the way to prove it by using Wronskian. The definition of the Wronskian is coming like this. The Wronskian is just the determination of the function that you have. For example, if you have n functions, f1, f2, until fn, Wronskian defined as the definition, the determination of the function n and the derivative of each function until the term of derivative n minus 1 of each function. Okay? This definition means the Wronskian of function f1 to fn. And the way that we define from this is that if we know that Wronskian of our y1 and to yn, because we said that y1, y2, y3 into yn got to be linearly independent to each other. We are going to use the Wronskian of y1 and to yn to see whether it is really independent. It said that if we find that the Wronskian of that function equal to 0, it means they are linearly dependent on each other. But if the Wronskian is not equal to 0, any number which is not 0, then that means all y, y1, y2 to yn are linearly independent. So if you prove that Wronskian of your answer is not equal to 0, that means they all are linearly independent to each other, then you can write down the solution, the general solution of this equation as yc equal to c1 y1 plus c2 y2 plus until cn yn. That would be the way to get the answer for the n order linearly homogeneous differential equation. Any questions? Now you don't know how to find y yet, but you've got to understand the basic idea of this first. For example, if they already give the solution for you, like prove that y1 equal to exponential of minus 2x and y2 equal to cos x and y3 equal to sin x are the solution of this differential equation. If so, write down the solution, the general solution of this differential equation. This is an example, okay? Now, if you look at this differential equation, you would find that it is a linear differential equation. And it is a homogeneous equation, right? Because fx is equal to 0. It is a homogeneous equation, right? What would be the order of this differential equation? Order of 3. So order of 3, you've got to find 3 answer of y, which is the problem statement itself just gave to you, and asking you to prove that y1, y2, and y3 here are really the solution of this differential equation. So we got to prove that first, okay? We are going to prove y1 is the answer, whether it is the answer. So the way that we do is just plug y1 into this equation. If you plug it in there and then it makes equal to 0, that means y1 equal to exponential of minus 2x is the answer of this differential equation, right? But when you look at this equation, you've got to do differentiation of y1 3 times, right? Right? Because in this equation, you've seen the order of 3, the order of 2, and the order of 1. And why? Why you know this? So you've got to find the order 1, order 2, and order 3 of this y1. Okay, so we get to do it the first time of derivative y1 equal to what? Minus 2 times exponential of negative 2x. If you do the second time of it, you would get what? Plus 4 times exponential of minus 2x. And you get to do it one more time, right? Because in the equation itself, you have 3 times, right? So the third time, what you get? Negative 8 times exponential of minus 2x or negative 2x. And then you just plug each term into your differential equation, you would get minus 8 plus 2 times 4 plus minus 2 plus 2 times, it is really equal to 0. You see this term and this term, they all sum together equal to 0. These two terms, you sum them, you would get 0 too, right? So 0 equal to 0, that means means y1 is the solution of this equation. Now we do y2. y2 is equal to cos x. Again, just repeat it. Just do the same as y1.